All right, here we go. Last day, y'all. Long time coming. Well, last day for class. You guys still have to, those little pesky finals. I mean, what, what's the big deal about that, right? So let me pray and then we'll kind of get going here. Father, we're grateful to be here. We're grateful that you have brought us to this moment. You are good, you're faithful, Lord, and even in hard times, you are faithful to teach us good things about ourselves and about yourself. And Lord, how best we can live our lives in the light of who you are. So Lord, I pray that you would empower us to do that, even this hour. Pray that we would have good discussion, that our minds would be engaged, and that we would learn much. Pray these things in Jesus' name. Amen. All right. So just a brief review of what will be expected of you on Wednesday again. Wednesday, 4/28, which is my birthday, by the way. That's amazing. Oh, wow. Yeah, so 10 a.m. to 12 p.m. I get to, on my birthday, celebrate that by giving a bunch of finals. Okay? What's that? Yeah, that's right. So you can have an 8.5 by 11, 8.5 by 11 inch, not feet or whatever, with whatever you want written on it, front and back. Believe it or not, I do have to specify things like that. Okay. Again, chapter 15 will be a chief emphasis on the exam itself, but don't be surprised if I ask you stuff from chapters 13 and 14. Okay. Now remember, we kind of went through this nutshell description of what we've done this semester. Chapter 13 was primarily an introduction to multivariate functions, graphing of surfaces, differentiation of multivariate functions, things like tangent planes and whatnot came into our cognition, right? Chapter 14 was exclusively focusing on the integration concept, and we were really trying to understand what was going on there. And then chapter 15 is like the vector analysis application side of things, okay, which most recently culminated in the Divergence Theorem and Stokes's theorem. Now, one thing that you should have discerned by working through, the section on surface integrals is that surface integrals are incredibly annoying. If you have to do them from scratch, with a parametrized surface and then just go through the motions of trying to compute these surface integrals, it's a little bit painful. It really is. I got to be honest with you, okay? But these two theorems give us ways to kind of get out of it, especially Gauss's theorem for sure. Because remember, Gauss's theorem says, oops, what am I doing? I have to be over here to do this, okay? Gauss's theorem says that if you start with a closed surface, that is a surface which encloses a solid, yes? If you start with a closed surface with an outward oriented normal, and D is the solid bounded by S, then the surface integral for a vector field over that surface is given by the triple integral over the inside of the divergence of that vector field, okay? That is gold, that is pure gold, believe me. That really makes your life simple, because there are sometimes when you will have surfaces, like for instance, a cube. You'll have like a cube, okay? And a cube, or like a rectangular prism or something, yes? Think about it. How many faces are there on a cube?
8.
No, not 8. There are 6, yeah? There are 6 faces on a cube, yes? And you cannot parametrize all of those faces simultaneously, don't you see? You would have to split it up into like 6 separate surface integrals, which is a nightmare. But the divergence theorem says, hey, you only have to do one integral, namely this triple integral right here. Okay, so that is fantastic. Okay, and we did this nice little example last time that helped us to that end. Stokes's theorem says something a little bit different. It kind of relates a curve integral around a closed curve to a surface integral, right? So I have a surface that doesn't enclose a solid necessarily, yeah? So this thing kind of stops like this. I have this boundary curve. I have the upward oriented normal that induces kind of a counterclockwise rotation around that curve. If I'm looking from it, looking down on this curve, it would be counterclockwise, okay? And Stokes' theorem says the integral over that boundary curve with positive orientation, the line integral of f, the vector field you're looking at, is given by the surface integral of the curl of f dotted within ds. So it's a surface integral of curl of f over that surface with the upward oriented normal. And you might say to yourself, haven't we learned our lesson that surface integrals are bad and annoying to deal with? Well, the thing that kind of saves you here, though, is that instead of dealing with f, as you are in the line integral case, what are you dealing with in the surface integral case? The curl. And sometimes the curl is far simpler than the original vector field itself, okay? Sometimes the curl will actually end up being 0, and you'll be like, oh man, that's just 0, okay? And by the way, that's exactly what we mentioned last time. If f happened to be a conservative vector field, then it is irrotational, which means the curl would be 0. Don't you see, right? So we can kind of see immediately that this curve integral yet again would be 0 by Stokes' theorem if the vector field is conservative. We left off last time with this little problem right here that I want to finish working through. And let me just tell you, if you go into WebAssign, you do have a homework set on 15.6 that is due on Tuesday. That's tomorrow at midnight. But there's another one. I put a due date on it just because I have to in order to schedule it, but it's just for you to practice. It's just a few kind of problems from 15.7 and 15.8 for you to practice. Maybe we'll do 1 or 2 of those, but all of them, I am telling you, so it's just kind of applying divergence theorem and Stokes theorem. Yes, divergence theorem, Stokes theorem, okay? Over and over and over again. But we were in this thing right here, and we were starting to draw this picture, and we kind of ran out of time. Okay, so I want to compute this line integral f dotted with dr, where f is given by that vector field x, y, z, the first coordinate, y in the second, z in the third, and s is the first octant portion of this guy right here. And I said, look, I don't want to cheat and actually look at, okay, I don't want to cheat and actually look at, you know, what's it called? GeoGebra. Yes, I actually wanted to do this by hand, okay? Because I think that's a helpful exercise. One way that you can get an idea of what a surface looks like is to look at how it intersects various coordinate planes, okay? At least the portions that you happen to care about, okay? Okay, so look, what does z equal to x squared minus 3y? What does that look like? Let's see here. What does that look like over in the xz plane? Okay, what does that look like over in the xz plane? Okay, so I mean, in case you forgot, x is coming out at us, y is kind of going to the right, and z is straight up like that. What would this surface look like in its intersection with the xz plane? That's a question. Yes.
Upward, or the z upward facing parabola.
Yeah, right. It would be the parabola z equal to x squared. Don't you see, right? So I would get this parabola, and I'm just going to draw the portion that happens to be right here. Okay. So this is what that curve would look like here, and I'm going to chop it off right here at A. Okay. So this is this thing right here. I don't know. Let me say that's z equal to x squared. So that's what that part of the surface would look like. Now, what does it look like? Okay, what does it look like down in the xy plane? And by the way, how do you guys? Somebody tell me, not Jason or not Paul. Somebody tell me what that curve, or how did they come up with z equal to x squared? What do we do to get that? This is not a trick question. Yeah.
So y
You just set y equal to 0. That's it. Right? Set y equal to 0 and you got it. That's exactly right. Okay. So look, if I want to look at the intersection of this thing in the XY plane, what am I going to do? In the XY plane, set z equal to 0. Yes. Okay. If I set z equal to 0, interesting. Okay. So let's see here. I'm gonna use green for this one. If I set z equal to 0, I get x squared minus 3y equals 0, which is the same thing as y equal to 1/3 x squared, which is again kind of a standard parabola down in the xy plane. But I'm only going to draw the portion that I care about, which is going to be, I don't know, like right here or something. Okay, do you see? Okay, so this right here is the curve, and I'm only drawing the portion that happens to belong to that x squared plus y squared equal to or less than a squared, that quarter disk of radius a, since I only care about the first octant. Okay, so this is the curve y equal to x squared over 3. Okay, and then finally, okay, last but not least, we're going to go ahead and look at what's happening. We're going to look at, okay. I really don't want to mess this up. So far, this picture is pretty clutch for sure. Okay. This is the x-axis, this is the y-axis, and this is the z-axis. Okay. What's going on over in the, okay, let's see. I'm going to pick a different color here, like yellow. Yes. Okay. What's going on over in the y-z plane? Y-z plane. Okay. What would I do to find out what's going on in the YZ plane? Yeah, right. You set x to 0. If you set x to 0, you get z equals -3y. Z equals -3y. That's seriously, that's just a line of slope -3 where y is the independent variable. Don't you see? Yeah. Okay. So that's not too hard to imagine what's going on there. I'm going to kind of I'm going to cheat a little bit, and just because my picture isn't exactly to scale, but I'm going to say, okay, so this thing, you know, kind of goes like this, I guess, right? So, okay, so this is, you know, and I'm going to kind of go up right here like this. This is z equal to -3y. Okay, and now we kind of have a little picture of what the surface looks like, right? You see what it looks like? I mean, you can kind of imagine how this thing is. I mean, it probably goes down over to here, and then it kind of goes down over to here. Okay. And overall, you know, does its thing like this. Okay. So I have my surface right here. There's our surface. Okay. Our surface is sitting right there. That's the surface. Okay. And the curve is the boundary of that surface. The curve is the boundary of that surface. Yeah. Okay. And okay, so I have the curve that happens to be the boundary of that particular surface. And it's going to have the positive orientation, which means as I look down on top of this, right, because look, it's the counterclockwise orientation. The positive orientation means that as I look down on this, the thing is going around in a counterclockwise direction. Yes, like this. Okay. So that means it would be going like this. Okay, so there's our curve right there. Okay, so here's our curve C. Okay, our curve C kind of goes around like that. And S is I won't try to color in everything because I don't want to mess up my my green curve and whatnot that happens to be intersecting with the XY plane. I want you to see all of that all at once. Okay. All right. So if I want to do this, okay, if I want to kind of compute this thing once and for all, now that we've kind of thought this through, the integral over that curve C, f dotted with dr, okay, that's going to be the double integral over S, well, the surface integral, not double integral, the surface integral over S, curl F dotted within d capital S. Yes? Okay. Okay, now remember that we have our surface looking like this, correct? and I want the upward oriented normal. So remember, how do we get the upward oriented normal? Do you remember? If I have the equation of the surface right there in hand, z equal to x squared minus 3y, how do I get the upward oriented normal? Do you remember we did something like this? We created a function of 3 variables. We subtracted things over. Z minus x squared plus 3y. We realized that this surface up here, this surface up here is really just a level surface, g of x, y, z equal to 0. And therefore, what will be perpendicular to that? What will be perpendicular to that? Since this surface is the level surface of this function we just wrote down, what will be perpendicular to that? The gradient. Yeah. Okay. Yeah. The gradient of capital G is equal to, and the reason I did z minus is because I want the upward oriented normal, yes? Z minus makes, like when I take the z derivative in the third coordinate, it's going to be 1, which means it's going to have upward oriented normal. Okay, so look, the third coordinate is obviously going to be 1. The first 2 coordinates, the x derivative is negative 2x. And what else? What's the y derivative? 3. Oh, wow, that's sort of convenient, yes. Okay. And remember, when we do this business right here with dotting within ds, we normally would have to normalize that thing. We would have to make it have length 1, but then the ds part also has that same length in it, and they cancel, yes? Okay. We also need, so by the way, these 2 things are absolutely taken care of by just the gradient of g in this case. Okay, so what about curl of f? Let's think about the curl of f. Okay, what is the curl of f? Well, that's going to be the determinant of this thing, right? I, j, k. Okay, and I have partial x. Oops. What was that? Partial x, partial y, partial z. And then I have, what was my function again? It was x, y, z, y, and z. Okay, so x, y, z, y, and z. All right. Let's see what happens here. Oops, I don't need that thing anymore. Let's see what happens here. Okay. Well, in the first coordinate, think about this. In the first coordinate, I cross out the first column and the first row, and I go partial y of z minus partial z of y. Hey, what are those going to be? That's going to be 0. Okay. Interesting. Okay. Then I do the y coordinate, and I always kind of do it backwards, okay? Just because you have to negate the second coordinate. I do it kind of backwards. So cross out the second column in the first row. That's going to be the partial z of xyz. What's the partial z xyz? xy minus partial x of z, and that's just 0. Okay. Finally, what do we do? What do we do last here? What do we do last? Okay, so we cross out the third column in the first row, and we go partial x of y, which is 0, minus partial y of xyz. Okay, so it's going to be 0 minus partial y of xyz, which is, what is it? xz. Okay, so we have our curl. It is 0, and then we have xy, and then we have minus xz. There it is. Okay. So we have our curl, we have our normal thing, but the thing is we also have to think about the surface itself. How do we parametrize this surface? What are we going to do to parametrize this surface? Well, we go R of, I mean, in this particular case, for crying out loud, the thing is already solved for, Z is solved for in terms of X and Y. So I might as well let my parametrizing variables just be X and Y, right? X and Y will be my parametrizing variables. To get on the surface, I just let Z be equal to what it's equal to in terms of X and Y. Okay. Okay, so R of XY, so this is us parametrizing the surface. R of XY equals X, Y, and what? What's Z? Yeah, it's just X squared minus 3Y, exactly right. Okay, oops. Okay, vector. Okay, now we have the curl. We have, we have everything we need at this point. Look at this. We have the curl, it's right here. We have our normal vector dotted with, or we have our normal vector and we've kind of taken into account the ds piece. The only place we're really going to have to think about, okay, because this guy is Z right here, we really need to plug in X and Y for X and Y, which is sort of stupid, yes. And the only thing we have to think about is plugging this Z in right here, right? Yeah, okay. So what's curl of F? So hang on, let's kind of start to do this computation. So this is going to be curl of F dotted with this thing. Okay, so first of all, we're going to double integrate over this region. X squared plus Y squared equal to or less than A squared. X and Y both greater than or equal to 0. That's the region, the quarter disk that we're going to integrate over. I'm just writing down what we're integrating over. Curl of F, that's going to be 0, comma, X, Y, comma, negative X, okay, what's Z equal to? X times X squared minus 3Y. That is Z. That is Z. Okay. So there's that. And I'm going to dot this with the gradient of capital G. Okay. I'm going to dot this with the gradient of capital G, which is negative 2x, 3, 1. And this is dA. Okay. Okay, just so that we don't have to like keep referring to this thing, I'm going to call this region right here R, okay, down in the XY plane. Okay, so this is going to be the double integral over R of what? What am I going to have here? Well, 0 times negative 2x, that's gone. I'm going to have 3 times xy when I take this dot product. And then I have minus x times what? Minus x times x squared minus 3y. Don't you see? What's going to happen here? What am I going to end up getting here? If I distribute that minus sign, what do I get? It's going to be negative x cubed, 3xy plus another 3xy is how many xy? 6xy. Okay, so it's the double integral over R, 6xy minus x cubed dA. All right. And now we're just back to chapter 14. We're just doing this integral over this little quarter disk. Now there are a couple of ways you could proceed. You could just keep this thing in rectangular coordinates and move forward. Yeah. But what else could you do if you really wanted to? What else could you do if you really wanted to? You can convert to polar coordinates, correct? You could convert to polar if you wanted to. I don't know. Let's just for practice do that. Okay, so let's see here. This would be x is r cosine theta, y is r sine theta. Yes. So I mean, if you wanted to see this kind of play out, this would be 6 r squared cos theta sine theta minus r cubed cosine cubed theta all times r dr d theta. And what would r and theta go between to kind of intercept this quarter disk? What does theta go between? 0 and 0 and pi/2. And then if you take any angle theta between 0 and pi/2, r goes between where and where? 0 and then the radius of that disk, which happens to be a. You could do it that way. You could have also done it just using the rectangular coordinates, but either way you could have pulled this off. Okay. I won't go through the computation there. It's not too bad. I don't see any like obvious tricks to make this thing totally trivial or anything like that. But this is still something that you would be able to do, hopefully. Yeah. Yes.
If you kept it in rectangular, would you just find the bounds from like the shadow and XY?
Sure. Right. So I mean, here we could do that fairly easily. You could just say that this would be equal to integral, okay, 6xy minus x cubed. Let's do dy dx. Okay, what numbers does x go between? What numbers does x go between to actually intercept that quarter disk? 0 and a. And as x goes between 0 and a, for any one of those x values, y goes from 0 up to the disk itself, yes? Or up to the circle itself. So the y bounds would be from 0 to, what's the formula for y when it's up on the circle? The square root of what? Yeah. Okay, so that would be the upper limit. Now, the one thing that has me concerned about that is that after doing the first integral, you're probably going to have some kind of gnarly square root in there, yes? Which would then likely require what? Trig substitution, okay? Maybe not, I'm not sure, but I suspect that you might need to do trig substitution. So to me, you could have proceeded that way, but this integral that involves the polar coordinates is not too bad, okay? I mean, it's fairly simple, especially easy in R. For theta, this first integral, cos theta sine theta, that's just an easy substitution integral. How do you integrate cos cubed? Well, to change the cos squared to 1 minus sine squared. Remember doing stuff like that? Yeah. Change one, write it as cosine theta times cosine squared. Change the cosine squared to 1 minus sine squared, and then you're off to the races. Yeah. That'll work out pretty easily. Okay. All right. I wanted to go over here real quick. Oh, by the way, let me just say equals, etc. We won't go through the rest of the computation. So equals, etc. Okay. But it's at least set up to something that you did back in chapter 14 for sure, with great gusto. Okay. I wanted to go back. Oh, and by the way, let me just say, how many curves, if we would have done that thing like the old-fashioned way, how many curves would we, like if we would have just done the actual curve integral around the boundary, how many curves would we have had to split that thing into? How many curves would it have been? Like the boundary of that surface, how many curves were involved? 3. You would have had to do 3 separate curve integrals. Don't you see? Yeah. So in this case, it seems like it was easier to do the surface integral itself. Yeah. Because you only had to parametrize one surface as opposed to 3 separate pieces that made up the boundary of that thing. I wanted to go in here and kind of look at this though. So like, look, there's one feature in GeoGebra I maybe haven't made as big of a deal about as I should have, but there's actually conditional things you can do in GeoGebra. Like if I write if, you can input a condition and then say what z is equal to when that condition is met. Okay. So like I can say things like if x squared plus y squared is less than or equal to 4, and, okay, I put two ands and it makes a little and symbol, okay, for those of you that love computer science, okay? That's the and symbol. If you put two ands in a row, it will convert that to a logical and. If x squared plus y squared is less than or equal to 4, I don't want the entire disk though, I only want the quarter disk, right? So I also want x to be greater than or equal to 0, but I also want y to be greater than or equal to 0. That is the part that we're looking at. If that's true, then I want to kind of graph, I want to graph my little function. What was my function again? Was it x squared minus 3y or something like that, right? So x squared minus 3y, okay? Ooh, what is it? Oh, it's because it's over here. Oh, they have me nervous there for a minute. So there's z equal to x squared, yes. Okay, look, there's the y equal to x squared over 3 thing that we had. They chopped this thing off here. I probably need to zoom out a little bit so that you can see that it's over the quarter disk, yes. But there's the surface that we just had. Of course, ours wasn't quite as precise as this one right here, but that is exactly the sort of picture that we drew. Don't you see? Yeah. So z equal to negative 3y, there's that thing right there. That's kind of neat, right? So there it is. Any questions on that? Questions? Any questions? Well, let's look at a couple of problems from the WebAssign, shall we? Okay. So if I go in here and I click on WebAssign, let's try to look at least, a couple of these things in here. This will help us out. Come on now. This computer's well known for slowness. Okay. Okay, so here are these things right here. Again, this is just a review. This isn't going to be counted as part of your grade or anything like that. But look at this guy right here. Okay, it says verify the divergence theorem by evaluating that surface integral, okay? Which is sort of an interesting way to put things. But, okay. That just means that instead of computing the surface integral, what should we compute instead? And incidentally, if I wanted to compute the surface integral, how many surface integrals would I actually have to do in this case? 6. 6, okay? That is not something that's going to be pleasant. You understand? Okay? So this thing is assumed to sort of have the outward oriented normal everywhere, just so that you know, okay? So like everywhere you look, you should imagine that the normal vectors are kind of heading outward like this, okay? Okay, and out here, they're pointed outward, and even on the bottom, they're pointed downward like this, okay? So all outward oriented normals everywhere. Outward oriented normals everywhere in sight, okay? Well, apparently, by the divergence theorem, this thing is equal to the triple integral over the solid bounded by that surface, okay? Divergence of f dv, okay? Well, what is the divergence of f? What would I do to compute the divergence of f? What do I do? Yeah, Jason.
Take the gradient of that.
Well,
No, dot the gradient with.
right. So, well, you dot the del thing with that thing. Yes. So you take the x derivative of the first coordinate plus the y derivative of the second coordinate plus the z derivative of the third coordinate. Okay. So it's going to be partial with respect to x of the first coordinate plus partial with respect to y of the second coordinate plus partial with respect to z of the third coordinate, which is z squared dv. Okay, so this is all done over this thing. Okay, triple integral, and look, this is just child's play. I mean, think about it. This is a box, or it's a cube, where x, y, and z all go between 0 and a. Yes? Okay, so x, y, and z all just go between 0 and a. 0a, 0 to a. Oops, should be a 0 down here, okay? Okay, the partial with respect to x of 2x, that's 2. Partial with respect to y of negative 2y is negative 2. That's convenient, yeah? Partial with respect to z of z squared, well, that's 2z. Okay, and I don't care what order you put these in. This could probably, you know, dz, dy, dx, whatever you want, okay? It doesn't matter as long as you have all three and not repeat something twice like I just did, okay? dz, dy, dx. Well, what happens here? Integral from 0 to a, integral from 0 to a. Oops, I did that again. 0 to a. 2z, what's the antiderivative of 2z with respect to z? Z squared. And that's z squared over, right, just z squared, that's it. Evaluated between 0 and a, dy, dx. Okay. Which is equal to a squared, which is a constant. And it's just going to be the integral from 0 to a, the integral from 0 to a of dy dx. And what's this? This is good review. What's that going to give us? If I just double integrate the function 1 over what it now is just down in the xy plane, the square with side lengths a and a respectively, isn't that just going to give the area of that square? Yes. Okay, so what is that going to be? That's just going to be a times a, which is a squared. Okay, so in the end, we get a to the what? Fourth. Yeah, a to the fourth. You see how easy that was? It's a lot easier than having to parameterize 6 separate surfaces and do surface integrals for all of those, yes? Not only that, you would also have to think about, okay, what's my normal vector, my outward oriented normal vector on every single one of those surfaces? Those wouldn't be too hard to figure out just by thinking about it. You could actually come up with it fairly easily. In fact, like what would be the upward oriented unit normal everywhere on the top? What would that be everywhere? What's that? Yeah, that's just K. Yeah, 0, 0, 1. Yeah. If I wanted the outward oriented normal everywhere on that right side of the box, that would be 0, 1, 0 everywhere. Don't you see? Yeah. You could actually just write down what the outward oriented normal everywhere. But the whole point is we avoided all of that by sort of appealing to the divergence theorem. Let's just make sure that we get the right answer here. A raised to the fourth. Okay. And I always have to do this weird thing where I submit everything. Okay, just to see what's going on here. Yes, says it's right. Okay, so there it is. Okay, the divergence theorem makes life a lot easier for sure. Okay, any questions on that? Questions? Hopefully that makes sense. Okay. There we go. Okay, let's see here. What shall we do? Maybe we'll do one of these. Let's do one of these Stokes theorems right here. Okay, let's do a Stokes theorem application. Okay, so here I have triangle with vertices 2, 0, 0, 0, 2, 0, and 0, 0, 2. Okay, so let's just kind of draw a picture of what's happening here. Okay, 2, 0, 0. So that's right here. 0, 2, 0. And 0, 0, 2. Okay, so here's this. This is the triangle they are talking about. And if I were looking down on that, I would want the orientation. So what does it say for the orientation? oriented counterclockwise as viewed from above. So that would be like this. Okay, so there's my boundary curve. And by the way, there is a surface that this thing bounds. They don't even tell me what it is. Like I could put any surface in here, but I might as well take the easiest one, like the plane itself. Yes, this little plane right here would be a fairly good choice for a surface that curve happens to bound. Okay. So C is the oriented counterclockwise curve is viewed from above on that triangle. Okay. Now, what Stokes' theorem allows me to do is to actually recast this integral as a surface integral. Yes. By the way, that surface right there, what is that? What is that surface? Let's kind of write down what that surface is. Okay. S is given by what is that? What is that plane? I actually just put that plane on there. What's the equation of that plane? Yeah.
X plus Y plus Z equals 2.
Yeah. Okay. That would be easy enough to come up with, but that surface is bounded by that. Yeah. Therefore, another way to say that is Z equal to 2 minus X minus Y, correct? So how would I parameterize this surface? R of X comma Y equals XY, X, Y, and the third coordinate would be 2 minus X minus Y. That would put me right on that plane, correct? Now to do that, to do this line integral right here in number 6 that we're working on right now, to do that curve integral, how many curves would I have to split C into? How many curves would I have to split that into? How many curves would I have to split that? If I wanted to do this curve integral right here, how many curves would I have to split C into? 3. That's annoying. I have to do 3 separate curves. Don't you see? Yeah. But if I use Stokes' theorem, okay, which I am inclined to do, you know that this is going to be the double integral over that surface, which that curve bounds, curl of F, dotted within ds. Yeah? Well, let's compute the curl of F, shall we? Curl of F, okay, is equal to, let's compute it, I, J, K. All right, let's think about this for a second. So partial X, partial Y, partial Z. Okay, and what do I have here? 2y, 3z, and x. 2y, 3z, and x. Okay, what do we get for the curl in this particular case? Let's see here. Well, I cross out the first column in the first row. Partial with respect to y of x, well, that's 0. Minus partial with respect to z of 3z, which is, what's that? -3. Okay. And then I cross out the second column in the first row, and I do a little backwards action here. Partial with respect to z of 2y, well, that's 0, minus the partial with respect to x of x. What's that? -1. Okay. And what's the last thing? I cross out the last column. It's going to be the partial with respect to x of 3z, which is 0, minus the partial with respect to y of 2y, which gives us -2. Does that make sense? The curl is a constant. That's interesting. Okay. Okay, also, I mean, in this particular case, I could do the whole G thing. So G of X, Y, Z in this case. Let's see here. I'll go Z plus X plus Y minus 2. Okay, that's kind of describing that surface, and then this surface right here, that is just the level surface G equal to 0, yeah? So if I want the upward oriented normal, I could compute the gradient of G, which is, what is the gradient of G in this particular case? What do we get? Gradient of G is 1, 1, 1. How convenient. How convenient. And you know that you would normally have to like normalize that, but you also know that the ds part would kind of cancel that normalization. Yes, we've seen that happen before. Okay. So what are we going to do in this case? 1, 1, 1 dotted with this thing. Okay. And what, I mean, you're going to have to think about what we're going to integrate over. It's going to be over the shadow of that thing down in the xy plane, but it's going to be the double integral of this vector, -3, -1, -2, dotted with 1, 1, 1. Okay. This curve right here that kind of bounds the shadow of the surface down in the xy plane, that curve is like y equal to what? Help me out here. What is 1 minus x? Okay. So I don't know. Let's go dy dx here.
Shouldn't be 2 minus x.
Oh, 2 minus x. Thank you. Yes, 2 minus x. Okay. So let's go dy dx here. And let's kind of think about this. Okay. So let's see. What would x go between? Just to kind of write down the limits of integration. What would x be going between? 0 and 2. And as that's happening, y goes between what? 0 and 2 minus x. That's exactly right. Now, here's what's interesting. Okay, integral from 0 to 2, integral from 0 to 2 minus x. Here's the thing, when I take this dot product, I get -3 minus 1 minus 2. I get -6. I get a constant dy dx. So isn't that just going to give me, I mean, think about it. If I have the double integral of that constant, isn't that just going to be that constant times the area of that region? Yes? It's going to be that constant times the area of that region. What is the area of that region? So look, I don't even have to do any integration here. It's going to be -6 times the area of that region. What is the area of that region? Yeah, because it would be 1/2 base times height, right? The height itself is 2. The base length is 2. Yes. And so it's going to be 1/2 2 times 2, which is 2. Okay, so we get -12 in this particular case. Okay. And if we didn't make any mistakes, which I mean, I guess it is possible that we made a mistake, we should have the right answer sitting right here. So -12 in this particular case. Okay, -12. Okay, so let's kind of check that. And if all is well with the world, we will end up getting that one right, hopefully. Yes, -12. Woohoo! Okay, there it is. All right, so you should go work through some more of those, and that will prepare you well for the final.